Hi Julian, thanks for joining us here for our new series, No Coffee, No Research.
Good morning.
At CISPA, we've noticed that a lot of people can't really do a lot of research without having at least some coffee. So
yeah, this is true.
So Julian, you're a faculty here at CISPA. You're working in cryptography, and you have recently been awarded with an ERC grant where you want to make distributed systems and ultimately our critical infrastructure that is all around us more robust and more secure. So how secure is our critical infrastructure right now?
I would say not very secure in the sense that a lot of our critical infrastructure is very centralized, meaning that it's not robust against common attacks such as denial of service attacks, or just because they have central points of failures that can be hacked or shut off. And this happens from time to time, and then we tend to notice. Yeah.
Okay, so do you have any examples of where critical infrastructure has been hacked in the past, or?
Yes, for example, I mean, there of course, sometimes this just also happens because of random failures, right? But we see this from time to time. For example, I think in early 2023, there was this big problem with airlines where there were thousands of flights canceled, and this could be attributed actually to the flight booking system, global flight booking system kind of failing. And that's just one example of how, like, if everything relies on one central point of failure, and the central point of failure for some reason doesn't behave the way that it should, things can go really wrong. And the purpose of my research and my ERC project is to look at this critical infrastructure. I mean, arguably, I'm not sure if a global flight booking system would count as such, but you could make an argument for that.
I mean, supply chains, everything.
Absolutely, or online shops, something like Amazon. Anything basically that like millions or even billions of people use on a daily basis, and that's like in a remote or online kind of situation. So the project looks at these kind of systems and tries to remove central point of failures and tries to make them implement them in a distributed kind of sense. So instead of having one central point of failure, you distribute the workload over many different replicas, and they all together emulate the service together. And then we can guarantee that if most of them behave the way that we expect them to, so they don't crash or they don't start sending incorrect stuff, then everybody who uses the system actually has a consistent view of the system and has the functionality that they would expect. And so why is this difficult? Because as soon as you distribute something and you want to have a consistent view of what's going on in the system, then these replicas have to coordinate somehow. They have to see how the system is changing, and they have to adapt to it, and all of them have to keep this consistent.
They have to communicate their changes.
Exactly, and they have to agree on the changes, and this is a very, very difficult problem that's been around for a long time in distributed computing.
Okay, so you would argue that right now the status quo is, I mean, I don't know, there's always like this, we always have this image of, especially when it comes to industry, of some old computer that was built in 1980 and the code was written in 1981 that is still running the entire power plant, or so to say. And I mean, this might not be accurate in every case, but so you would argue that we have to remove this kind of very critical points that control a very large system and then try to move them to different places.
Exactly, like have some redundancy so that if part of the redundancy fails or becomes hacked, the system will still remain secure and operational. And so I mean, you could ask. I mean, there are algorithms that already do this, right? And so why are we not implementing them all over the place? The reason is that they're rather expensive. Okay. And so the problem is that in order to do this whole communication and everything, you have to exchange a lot of information. And I think until recently, maybe 10 or 15 years ago, this was just too expensive to ever consider a viable option, right? Because you have to maybe exchange gigabytes of data. Nowadays, we can't afford to do that.
So expensive, sorry, in terms of computing power or in?
No, it's just, well, also in terms of computing power, obviously there will be some computational overhead for sure. but also in terms of just communicating data. You know, like you have to, if there's a central point of failure, this can be a very, very powerful server, which has a lot of bandwidth, and it can send around all the data that's relevant and update parties. And if we trust the server, then we can all just talk to the server, right? Which is the central point of failure in my example. But now if you have a bunch of nodes and they all want to emulate the server, then they all have to send data to each other, and that makes things a lot more expensive. So this is where cryptography actually comes in. So very, very high level speaking, cryptography can do, well, it can actually do a lot of nice things for us, right? So first of all, like very fundamentally, you need cryptography to solve many of these distributed problems with a high fault tolerance. So if you don't have cryptography and you assume like arbitrary types of failures, so if you try to build a distributed system and the nodes in the system, they can start to behave in any way that you could or could not expect, they can do whatever they want, then you can tolerate at most 1/3 of them failing. Actually strictly less than that. And so if you bring crypto into the mix, then you can solve it for half of them failing, which is actually a significant improvement for many settings.
So if you have 10 computers, 5 could just do whatever they want. They could not contribute.
Well, it will be 4. It's not 5. Like 11, it will be 5. So it's like strictly less than half. You need, like intuitively, you would say you need a majority of the system to still behave honestly, right? So you can't do better than that. But with crypto, you can get to this optimal kind of resilience.
And then those computers could do whatever they want. They could even start contradicting everything.
Exactly. Yeah, they could do whatever they want. The system would remain secure.
Interesting.
So that's what crypto gives us, and this has been known for a long time, since the 80s, right? And there's a lot of algorithms which actually solve things like agreeing on a common view. They're quite old. They've been around for a long time, but I think it's only quite recently that we started to really look into how efficiently can we do this. How much communication do we have to perform to actually get this consistent view? And that's where things get very interesting, right? Because with like just very basic crypto, this turns out to be very difficult. So that's not really, I mean, I think we're making progress there as well, just using very, very basic types of crypto to still do this efficiently. But where it really gets interesting to me as a cryptographer is using advanced types of cryptography to solve these problems much more efficiently than what you could do with only basic types of crypto or with no crypto at all, right? And so by advanced types of cryptography, I mean, you know, very, very recent developments in cryptographic primitives, for example, fully homomorphic encryption, which lets you compute on encrypted data. So this is a very, very powerful tool to reduce communication overall, because you can do a lot of computation locally. You don't on the encrypted data without actually communicating it to everybody. Another thing that's very powerful is the concept of either zero knowledge proofs or proof carrying data. We also call them SNARKs. They stand for succinct, non-interactive arguments of knowledge. So what that means is that you can prove a statement, maybe that you saw some information that is relevant to the protocol, with a very, very short representation, and everybody can verify this proof and be sure that you didn't lie about this. And for example, you could compress a lot of data into this very, very small proof, and then you can show this proof to everybody else instead of that data, sending them that data directly, right? So this has had a big impact on how much you have to send in these protocols, right?
Okay. Yeah. So CISPA does a lot of research in a lot of different directions. Whenever I talk to cryptographers, I always have the feeling that even for computer science, cryptography is still the complicated part. It's the math part, basically. So, and it's very interesting that there's these in the beginning sound like very theoretical concepts, and now introducing them to actually have an impact on our society is what's very, very, very interesting to me.
I mean, that was always my view of cryptography, that it's a theoretical subject, but it's very close to practice. Because, and I think there are a lot of cryptographers that do research that is very close to practice, because a lot of the research that we do is trying to make systems more compact. I mean, it's also theoretical in nature, of course. We tried to reduce the assumptions, complexity, theoretic assumptions under which we can prove our systems secure. That's also a big part of cryptography. But in some sense, I think we always have most of our things that we build have a practical application in mind. So it's also, when you read the intros to our papers, usually they're always focused with some motivation in mind, and people really emphasize this in their papers, I think. Okay. I'm not sure if this is the same in even more theoretical areas. For example, complexity theory, which is really very theory driven, right?
Yeah.
And it's like, but yeah. So I mean, and obviously there is a lot of math involved. I mean, but what I like about cryptography is that there are so many different types of math coming together, right? So we use number theory, coding theory, probability theory. All of these things kind of come together and form like this nice field.
So looking into the future, how long do you think it will be until we can safely assume that our critical infrastructure is very robust? And
I can't make any predictions. I mean, I think there are two obstacles toward this right now. So I think one obstacle is just developing these systems in the first place, and then I think the other obstacle is that I mean, how do you get people to actually switch to this, right? So we've seen this huge effort by the NIST, the National Institute of Standardization and Technology, to switch to post-quantum cryptography. And like this big competition where many people around the world submitted their proposals for post-quantum cryptographic systems, and then they were evaluated, and in the end we have now a whole set of post-quantum secure cryptography systems which are being implemented everywhere. And I would say probably it's necessary to have similar kind of setup to transition from what we currently have to implementing these distributed systems on a wider scale. Yeah.
Okay, so it takes political initiative also to.
I do think so. Yeah, and I think like this having like this tournament kind of setup that they did, where it's a competition. I think it's very important because like a lot of these systems they're very, very complex, and like things tend to get overlooked, and then like later they're found. So this happens quite frequently actually, and I think going through these multiple rounds of checking again and again that everything is correct is very, very important. So,
okay.
Yeah.
Well, thank you very much. I hope you will stay as fascinated by math and cryptography as you are right now.
Yeah. Well,
and I'm looking forward to see all your cryptographic primitives being implemented into the real world and making it more secure. Thank you very much, Julian.
Thanks.